Yeah, my name's Dave Rowland. I am the CTO of the Audio Squadron Group. We have kind of two main sides to our business. We're an audio company to start with, and on the Prism Sound side of things, we make high quality audio hardware that's desktop interfaces and large channel count converters that are used in large studios. And on the software side, we have a bunch of synthesizers which make weird and wonderful sounds, and we also have a DAW called Waveform, and we open source the engine that runs on. If you're not familiar with a DAW or digital audio workstation, this is just a kind of overview of some of the screens you can see in Waveform. It's essentially a tool used for creating multi-track audio. So you might create a podcast or a band recording or some kind of electronic music. And the main overview is that you have a bunch of tracks going from kind of top to bottom. You have content on those tracks, which might be audio clips or MIDI clips, like from a keyboard. And they're in the middle. And then on the right-hand side, you can see a bunch of plugins, which will be either instruments or effects like compressors, delays, EQ. And then you arrange everything, and then you render it out to perhaps a stereo or multi-channel audio file. So I'm going to start today with a quote from Titus Winters, who up until recently, I believe, was a tech lead at Google, but it appears in the software engineering at Google book as well. And the quote goes, "Software engineering is programming integrated over time." And that sounds simple, but it creates an important distinction between the act of writing code, which is programming, and software engineering, which introduces a time element. So when you're writing code over time, you need to think about what can change. And I like to think of performance and take an engineering approach to that. So how is the hardware that you're running on changes? How are your users changing? There's all sorts of things that can change. So we need to continually monitor our performance so we can keep on top of it, really, and avoid any potential performance issues creeping in. So today's talk is going to be split into roughly 4 chapters. First of all, I'm going to do a quick overview of audio systems, just so I can share a bit of my background, and also it kind of sets the scene for some of the examples we'll see later on. Then we're going to look at the foundations of what might make a benchmarking system. Then we're going to look at some actual optimization techniques and some approaches to that problem. And then we're going to look at multi-threading and how everything, including CPUs and memory, kind of tie into that. So first of all, the overview of audio systems. Digital audio systems typically center around a computer, and on that computer, you usually have a piece of recording software like I just showed, and in that some effects or processors. And you might want key events in, so note up, note down events. That typically comes from a MIDI controller, but then at some point you want to get the audio out. So you attach an audio interface, and that converts the digital signals that the computer's sending out to analog signals that your speakers can output. And you usually want to get audio in at some point, like a microphone here, so or a guitar, and then that interface also converts the analog signals into digital signals that your computer can process. So in the analog domain, we typically think of audio as a continuous wave like this. And then the digital audio converter samples it, so we get these kind of discrete points, and that's how our audio is represented on the computer. But this doesn't happen kind of continuously as a stream. It's kind of chunked into buffers because that's an efficient way of doing it. So what we really end up with is the digital audio converter kind of sampling in chunks that can be sort of around 2 to 5 milliseconds long, typically 100 to a few hundred samples. But that's not happening just for the input path. That happens as you're outputting sound as well. And of course, the computer at the center is doing the processing on every block. So what we typically get is a blocking, processing, and then outputting a block at the same time. But you can't output the block that's currently coming in. So you have to introduce a block of delay, and we call this round trip latency. And what can happen is if your processing takes too long, you're not able to output your buffer of audio within the time deadline. And this is called buffer underrun or overrun, and it's heard as an audible glitch. You can see why if you look at the waveform, if we kind of pull out a buffer or just silence will be produced here, what you get is this large kind of transient from 0 to where the next sample is. And that may not seem a lot on this image, but it's really noticeable. Human hearing is really kind of adept at picking these things up, and they can be heard as either pops or clicks and sometimes quite loud. Why does this matter? Well, perhaps if you're this person who's at home creating some music using headphones, it might be a bit irritating and they might not be able to kind of hear their music very well. But imagine you're these people who may have spent a lot of money on tickets to a live show. If everything starts suddenly going pop and click, not only is that going to ruin the experience, but when everything's kind of amplified, it might also damage hearing. And it's because we have these real-time deadlines that we typically think of audio as kind of firm real-time. I spoke about this in detail with Fabian a few years ago at Meeting C++, if you want to check that talk out. But we call it firm because it's a serious degradation of service, but it's not complete system failure like it might be for, car systems or medical equipment. So we kind of live in the middle here. Okay, on to section 2. We're going to look at benchmarking and what we mean by that. So we're going to have the view here is to build a system to enable us to benchmark over time. So what are benchmarks? Well, effectively, they time the amount of time that it takes to run some piece of code, right, or to execute that code. And we do this in order to assess performance characteristics. And if we do this in a structured, repeatable way, then it means we can look for trends. We can identify regressions. So when performance gets worse, we can see this. We can measure optimization attempts. So if we're trying to improve the performance of a piece of code, we can see that that's actually worked. And also we can compare between environments. So if we're distributing to Mac and Windows and we optimize something, and we know it works better on the Mac, we need to make sure that it also works better on Windows and we haven't made a regression there. So benchmarks typically live on a sliding scale with micro at one end and macro at the other. On the micro side, we're typically measuring either a single component or task. And that means they're quite low level. So we can often think about the code in terms of instructions generated, cache misses, how it interacts with the hardware, that kind of thing. And I like to think of them in scope similar to unit tests, right? So it's that kind of amount of code that you're typically benchmarking. On the other end of the scale, we have macro benchmarks, and these typically measure a whole system or at least several components of a system. So they're much higher level, and we're typically measuring either the throughput, the amount of data that's going through our benchmark, or the execution time. And in terms of testing, you can think of these similar to integration tests, so that kind of scope. And because they're much higher level and we're measuring things like execution time, then we notice that they reflect what your users will see. So they might be things like in an audio system, we're trying to export our session. How long does that take? So there's a kind of a proper map into the user experience. Okay, so we know kind of what code we want to measure, but what data, what metrics do we actually want to get out of this? Well, if we measure our piece of code executing many times, not only can we find the total execution time, but we can find the minimum and maximum times, the mean, average, and the variance or the standard deviation. And each of these is useful for telling us different bits of information. The total execution time is useful for those macro characteristics, like I mentioned before, but max is useful for our worst case scenarios. So I mentioned those buffer underruns. If our buffer is, say, 3 milliseconds long and our benchmark is showing something's taking 4 milliseconds, then we know that we're going to get buffer underruns, and that's going to be a problem. Min is also useful because it tells you theoretically where you could be. So if you can analyze your code and say, well, why are the minimums not being hit in these situations? Then if you can bring those down, then you're likely to get less, bring the max down and get less underruns and problems there, generally improve performance. And mean gives you an expected indication. So again, it's useful in combination with the others, but it's what your users will see most of the time. Okay, so what do we actually record when we want to get these metrics out? Well, the first way we can do this is time. And by that, I mean, proper time, wall clock time. That's typically achieved using stood chrono and high resolution clock. And as I said, this indicates what a typical user will experience because it's proper time. But it's environment dependent. So if you're running on a CPU with a clock speed of gigahertz, and then your user is running on, I don't know, half gigahertz or 2 gigahertz, then the amount of time elapsed generally is going to be very different. So there's something else we can look at, which is the CPU timestamp. And that measures not kind of wall clock time, but the number of clock cycles that have elapsed. And there's a couple advantages to that. First of all, it's a lot less overhead to measure. We'll see a benchmark of that in a minute. But it also makes it easier to compare between platforms. We don't have that problem then if we're running 1 gigahertz versus 2 gigahertz. Theoretically, the number of clock cycles should be the same. Now, that doesn't hold true because different CPUs have different pipelines, different sizes of cache, and different instructions. So it's not going to be an exact mapping, but it's probably going to be closer, and especially if the CPU architecture is similar. So I'm going to show a lot of benchmarks today from a website called QuickBench. I hope many of you visited this. If not, it's kind of like Compiler Explorer, but it wraps Google Benchmark and helps you generate performance comparisons, basically. So here's a quick benchmark comparing our chrono high resolution clock now call, which we might do on macro benchmarks, versus our RDTSC call. And if you look at the comparison here, you can see RDTSC is about 100 times quicker. And that's typically because it lives in a register, so it's almost instant to access. There's no kind of overhead of function calls and so on. So when you're doing micro benchmarks, you might want to avoid calling stood chrono completely, or at least be aware that that measurement is going to be in your benchmark. Okay, so now we know what to store, we know how to get the time, and we know what kind of code we're going to be benchmarking. But where do we actually run these benchmarks, and where do we store the results once we got them? Well, we want stable environments because that enables us to repeat things over time and compare them. And ideally, this means constant machines. If you work in a very performance critical, sorry, I've just got Q&A. If you work in a performance critical industry, then so someone's just pointed out in Q&A that high resolution clock shouldn't be used because it's susceptible to time leaps and time adjustments. Steady clock should be used. Okay, yeah, sorry, I think I do use that. It was just a problem on the slide. Ideally you want constant machines because then you know that the performance is exactly the same over time. And if you work in an industry like finance, you might typically use an exact replica of your production machine just for running benchmarks. So you know if you make changes, then they're going to be replicated in production. Another way of doing this is to use cloud VMs to provide indication. So perhaps you don't have a budget to have a dedicated benchmark machine, or it's an open source project. You can use things like GitHub Actions, which give you pretty good results. And we'll see some examples of that later on. So once you've got all your results, you want to store them somewhere, and the best place to do this is typically a cloud database. And that's because it's very easy to view the results. The bit of this that I haven't yet implemented, and I mentioned this last time, I gave this talk about 6 months ago, or a version of it, and I still haven't got around to it, is automatic notifications. I would like to see performance treated in the same way as things like code coverage. So if you make a commit to your code base and the performance gets noticeably worse, then that commit is rejected and said, yeah, you need to pay attention to this. So I think that would be quite a cool feature. So if we put this together, we kind of have this rough system diagram. We first of all need to measure. And in the way we do this at Tracktion, as I've said, we do this on GitHub Actions using their runners. We have a couple of classes that run our benchmarks, and I'll go over those quickly. There's a whole bunch of different ones you can use, but I'll show you the general shape they take. Then we store these in an SQL database that lives on our servers, but there are lots of services available for this. And then a really simple way to view them is back on GitHub using GitHub Pages with just some simple HTML and JavaScript and a thin PHP API that lives on our server that returns the results. So typically when you're benchmarking, you have some kind of performance measurement class that has a start and stop method or function, and that goes around the bit of code that you're actually measuring, and it measures the elapsed time or clock cycles between the two. And then at some point you can get the statistics back out. And here we have both statistics being measured, the seconds, max, min, and total, and also the cycles are measured here. We want some information to be able to store these in our benchmark, so we have to create a description for this. I tend to group them into categories with a name, which is a kind of short form name, and then a description, which is meaningful. And also we store the platform so we can compare them between different environments. And we also need a unique identifier for these, which is the hash. What I found is quite useful is if you hash together the category, the name, and the description, then if the description or something else changes that's meaningful, like it might say something like exporting 30 seconds of audio with a buffer size of 512, if someone changes the benchmark and updates the description, so it's now 256, then the hash is going to change and it's going to be recognized as a unique benchmark, which is good because, suddenly your performance gets twice as bad and you start panicking. It is a different benchmark if you change what you're benchmarking. We wrap these together into what we call a benchmark result, and we add in a timestamp here so we can view these chronologically when we add them to our server. And then we just wrap this into an RAII class, which does our kind of start. This benchmark class groups all these together, and there's a kind of scoped benchmark that calls start and stop, and then also publishes it to a list that gets uploaded to the server on exit. We use the Juice framework at Tracktion quite a lot, and that has a unit test framework. So I just kind of hijacked the unit test framework for running these. I'm going to get rid of a lot of the kind of bloat that you don't really need to see, but effectively our test harness, we'll call this run test method, and then we run this run sampling rendering function with a different name and a different resampling quality, and then we just set the resampling quality. In our scope benchmark, there's the description and everything, just measures how long it takes to measure this piece of code. Now, this is a very macro level benchmark. We're just looking at total execution time here. We don't run it many times because it can take 30 seconds or so. So this actually resamples audio from 96 to 44.1 kilohertz with different qualities. And if we see the results on our kind of makeshift benchmark viewer, we can see how the different algorithms compare. So kind of going through from kind of top to bottom, left to right, the quality improves, but you can see also the CPU time takes a lot more. And this is useful for several things. If we, first of all, have a quick look at what we can kind of filter or adjust by, we can see we've got our categories, name, platform, etc. We can filter by start and end date, which just enables us to zero in on probably the last month is a good default, or much longer times. And then you can show the various metrics, so total, min, max, and the variance, and also normalize the graphs, which is useful. Because if we normalize them, we get a display like this, and we can see here that this is pretty constant, okay? There's a fair bit of jitter in the best quality, which maybe says, we probably don't want to use this as a user default because the mileage is going to vary quite a lot. But we might want to go for sync fast, the one in the bottom left, because that provides a much better quality step up from the Lagrange, but at not so much more CPU. So it's just nice to view benchmarks on graphs like this. It's been brought to my attention before that why didn't we use Grafana for this? And you probably could do. I wasn't aware of Grafana when I started writing this, and it only took me like a day or so to kind of hook everything up. I did look into Grafana recently, and it seemed to be really good if you have like just a few benchmarks that you want to look at all the time. But we have many benchmarks, and something a bit more custom just kind of fitted the bill a bit better. But certainly check out Grafana first because it might be a lot less setup for you. So when do we add benchmarks to our suite? Well, first of all, when we add new features, we should probably add benchmarks. Again, I like to think of them like unit tests. So when you add new code, you're probably going to write tests around it, write a quick benchmark as well, particularly if it's a performance sensitive piece of code. If we get reports from QA or users saying, this behaves a bit sluggishly, or this isn't completing in quite the time that I thought it would, then add benchmarks. And also when you see benchmark regressions, this can be an indication that if it's a fairly macro level benchmark, you might want to go in and split it up into a few more micro benchmarks to give you an idea of what is actually causing the regression. Okay, on to optimization. First, we're going to look at some tools for identifying where we need to optimize, and then some optimization techniques. So most of these are examples from our actual real-world code base. So how do we find out what areas of code we need to optimize? Well, we have our benchmarks, which benchmark different sections of our code. So if we run these under a tool, we can get an idea of what bits of the benchmark we need to improve. The tools come in a few different kind of levels. At the top level, we have time profilers, and these give you a tree of time spent in each functions. And I'll show examples of all of these, so don't try and visualize them too hard. And these can be used to identify code hotspots. And they come with all the major tools. In Xcode, you have Time Profiler. Visual Studio comes with a Profile tool, and Intel has VTune, which is available on all major operating systems, I think. A level down from that, we have system tracers, and these show events such as system calls, memory management, thread interruptions, etc. Things that the operating system is how it's interacting with your code. And again, there's tools in Xcode called System Trace, and then on Linux you can have dtrace and strace as well. And then at the almost lowest level, you have performance counters, and these read CPU hardware registers for things like branch mispredictions, cache misses, and so on. And again, Xcode has a counters tool for this, and on Linux you can use perf. It's important to know that when you're trying to optimize code, that you want to profile your release builds. If you profile debug builds, you're most likely going to be profiling things like assertions, contract checks in the future, which would be nice, login, and also the optimizer doesn't have much of a chance to run. So things might be inlined and then kind of optimize out of existence, and constant propagation happens, and all sorts of nicer instructions are generated with high levels of optimization. So always profile your release builds, except if you're trying to speed up your debug experience, which is a thing you do sometimes if it's becoming unusable. So here's what a time profiler looks like. As I mentioned, we get that tree here, and if we zoom in and we were trying to optimize this piece of code, we would say, okay, well, about half the time is spent creating MIDI clips in that constructor, and then about half that time again is spent calling quantization type update type. So those are good targets for optimization. We want to go into those and see what they're doing. You can see we've got lots of string allocations and operations there. So that's probably the first port of call here. Onto system traces. Rather than getting the tree, we get a narrative here of essentially system events. And we get quite a lot of information. So I've zoomed in quite far here, and you can see that first of all, we have some virtual memory faults. So these are happening in your real-time threads. That's a cause for concern. You can also see your thread states, so when they're running, when they're paused, and also what interrupted them. So it might be that a mutex or some interrupt handler stopped your thread running. You can also see in here what cause they're running on. So that might be useful if you're looking to optimize cache misses and things, very low-level cache that lives on the core. And finally, you can see things like system calls. So here we can see highlighted, we've got stat, open, read, close. Those are file operations. So again, a definite no for any kind of real-time threads. Finally, we have the performance counters. And here you get the tree again, but you also get these new columns where you can see your branch mispredictions. We've got enabled level 1 cache misses and level 2 and level 3 cache misses. So if you see lots of branch mispredictions, you might want to go in and change the order of your if and else, or maybe reduce the amount of logical branches in there to improve those. Level 1 cache misses, all the cache misses we'll talk about a bit later on, but you can see here we get quite a few level 1s. Then the level twos creep in the middle, perhaps because we're operating on more data. But the ones we really need to worry about are level 3 cache misses that creep in here in about the final third. And the reason for this is best demonstrated with this animation. Now, I think Mike Acton gave this originally at CPPCon about a decade ago. I've seen Scott Myers do it, and I've used it before, but it really is the best way to visualize why this is problematic. So if we look at a level 1 cache miss, that's typically only a few cycles. It happens pretty instantly. A level 2 cache miss, however, it's about an order of magnitude on that, so it feels a bit slow. But if we look at how long RAM takes, it seems to take an absolute age. So we really want to try and avoid dropping off our top level cache, because if we end up in RAM, it's going to be really slow. And instantly, if you run out of RAM and it gets paged to disk and you end up having to do a disk read, then this could be around 10,000 times longer than this, or in this scale, a couple of days. So this brings us nicely onto a question about cats, and that's, how do they jump? Well, here's one of my cats, Aiko. You can see there that she jumps almost entirely with her back legs and just uses her front legs to kind of tuck in. This is my other cat, Eric, who's actually sitting behind me. I don't know if he's on camera, but sorry for the dark cat on the dark background, but hopefully you can still see him. You can see he takes his front legs off completely and just bounces with his rear legs, and again just spots his landing. So there we have concrete evidence that cats are rear-wheel drive. Okay, so now we're going to look into actual techniques for optimization. So the first one is to identify work that can be simply removed, because the simplest form of optimization is just not doing some work. Right? And the way we typically approach this is to use a profile trace to identify sections of code that just don't need to be run. This happens more often than you think. One common way of doing this is to spot memory allocations and just avoid doing them by reserving memory up front. Or you might need to think of an alternative approach in order to remove a chunk of code. And there's a few ways you can do this. We can do things like evaluate lazily, and I've got an example for that later on. Or also, more in kind of graphics programming, we do this, evaluating asynchronously. So that's when there might be multiple changes and you just kind of post a message off to be called in the future, which will do all of those changes in one go. So not every time something has changed. Okay, so here's a quick benchmark for essentially creating a vector of zeros. This is slideware. This isn't a real world example, but it illustrates a point. So I'm going to get rid of the quick bench boilerplate. And we can see, first of all, we're just creating a vector and then pushing back 1,000 zeros into it. Next, we're saying, well, why don't we reserve space for those 1,000 zeros? And finally, we know there's a constructor for the vector that can initialize and reserve in one go. So let's see the performance benefits of doing those optimizations. And yeah, we get roughly a 2 times, a bit better than that, speed up each time. So there's some good simple wins if we can identify those situations. Second technique is to identify work that can be combined together. And there's 2 main different ways of doing this. The first is to combine work in time, and that could be to evaluate it in parallel. So that means using multiple threads and hopefully multiple physical cores running those threads to do work parallel. And then the other way of doing this is to use SIMD instructions. So that stands for single instruction, multiple data, where you actually process 4, 8 more pieces of information with a single instruction. The other way of combining work in time is with a different algorithm choice. So in audio, we often draw those waveforms that I showed at the start of the talk. And the way we do this is we get quite a lot of audio data, typically about 100,000 samples a second is quite common. And we can't show all of those samples on the screen. So what we do is we figure out the amount of time or the number of samples a single pixel is going to take, find the minimum and then the maximum in the data, and then just draw a straight line between them. And algorithmically, this is kind of like a call to min element and then max element. But actually, there's an algorithm that does both of those in one go called min-max element. I've got an approximately equals here because they actually return different iterators if the same data value is found multiple times. So just be aware when you change algorithms that things might change subtly. back to SIMD examples, Fabian gave this really long, nice post on the Juice forum about how to try and get the auto vectorizer part of the compiler generating vector instructions for you. Not going to go into all of it, but it's worth a read if you want to. But essentially, he says you need to build with at least O3, and you need to relax IEEE compliance, and that's often done with the -F fast math flag, or you can get both of those with -O fast. And the reason you need to do this is, first of all, tell the compiler to spend some time doing it with the high levels of optimization, but also vector instructions don't conform to IEEE compliance because they can deal with rounding slightly differently because they work on multiple data at the same time, kind of rounding propagates slightly differently, and also they treat things like nans and imps differently, and we'll see an example of that. The other thing is that vector instructions typically only work on aligned data. So if the compiler generates them automatically for you, it will have to do some checks on your data and see if it's aligned, and perhaps you generate some different code for an unaligned section versus an aligned section. And that can add bloat to your binary. And there's actually a new feature in, I think it's C++23 called assume aligned that tells the compiler, no, don't do those checks. I'm guaranteeing that this data is aligned, which can reduce the size of your binary and perhaps your instruction cache pressure. So that's one to look out for the future. So I mentioned that infinities are dealt with differently. And this was an example someone pointed out to me that they had in their code base where they were dealing in polar coordinates and they were using infinities to represent boundary points on that circle. So when we compile normally with Clang, we can see that we create an infinity using std numeric limits, and we call it a std isinf, and then is finite to check if it's properly detected, and we can see, yep, it's an infinity, and therefore it's not finite. However, if we add the -F fast math flag, we can see that the output is that inf isn't detected, and therefore it's considered finite, which is obviously wrong. And the same happens on GCC. So just be aware that these things can happen when you're using vector instructions, and test, right? Test that you're getting the correct results. So here's an example of kind of using the auto vectorizer to do std transform. Here we're just copying two buffers together, or adding them up together, sorry. And we can see that we get roughly a 4 times improvement. That's generally what you'd expect, somewhere between 3 to 4 on most modern architectures, but up to 8 with much more modern architectures. So these are real easy wins for just a compiler flag. We look at that algorithm example that I showed. We get 2 calls to min and max element into a single min-max element. We can see that on GCC, we get nearly a 2 times speed up. That's a good win. And the same if we use Clang 15 with libstd C++, again, 2 times performance improvement there. But if we switch to libc++ and Clang 14, because I couldn't get it working with Clang 15, we see that min-max element actually takes more time. That's counterintuitive, but sometimes it is the case. And the reasons for this could be that perhaps it's loading more data, so there's more cache misses. It could be that the algorithm is more complicated, so the branch predictor can't train itself appropriately, or it could be the instructions aren't able to be pipelined as well. So, we need to benchmark to actually know that these algorithmic transforms we're making still give us the benefits we expect. Incidentally, I tried this again yesterday with Clang 17, and we're back to that almost 2 times improvement. So yes, these things change over time. Therefore, you need to measure your benchmarks over time. Okay, into reducing algorithmic complexity. So again, we typically find the areas that we want to improve using profilers and hotspots, and then we can look at try and reworking those algorithms. When we think about algorithmic complexity, we typically think in terms of big O notation. These come in various forms. We have constant time, that's where execution time doesn't vary with your data size. Then we have O log n, where more data leads to a decreasing increase in your execution time. Then we have a linear proportional relationship. And then really bad, we get into the exponentials, kind of squared and cubed, etc. If we change our algorithms, we need to make sure that we get the same results. And that includes our contracts, right? Our pre and our post condition. And of course, writing tests around these things saves us time. So here's an example, again, from our code base. I don't know if you can kind of remember the screen that we saw at the start of our software, where we have lots of things on the screen, lots of tracks, clips, and plugins. Each of those has a unique identifier called an item ID. And when you do something like copy and paste, you're copying perhaps hundreds or thousands of these things and generating unique IDs in a very short space of time. So someone reported this as a problem. It was taking several seconds to copy and paste their project. So I looked into what was taking the time, and it was this function. So I thought, okay, well, what is it doing? The first thing we can see is there's a note here that says this may be slow under heavy load. Keep an eye out for this in case a smarter caching system is needed. It's kind of annoying because if you knew it was going to be slow, why didn't you make it faster? But in all fairness, it's using the rules of optimization, which is no premature optimization. So, okay, fair enough. But what it's actually doing is we have this state object, which is, you can think of it as like a live XML tree, and it iterates through recursively, looks for each of the properties to see if they're an ID declaration, and if they are, converts each of the values into an ID and then adds it to this array. So it's kind of like a really complex operation for every time you want to generate an ID. It's a bit more complicated than that, though, because if you're doing something like a drag and drop between different bits of UI, then the thing that you're dragging might not actually be in the model. So we have a bunch of other ways of adding those into the found IDs as well. So once we've got all the IDs, we're going to sort them, and then we're going to go through and try and find the first space. Okay, so if we have 101 and 103, we're going to find 102 and then use that as the identifier. So I thought about this and I thought, well, we just want to create a unique identifier. So surely we can just increment our ID counter. And next ID is essentially just an integer. So this is really cheap to do. So I did that, and I added an assertion to check that it works. But we need to know where to start our count from. So the first time we do this, we do something similar to before, except for rather than finding the first gap, we just jump to the end because we know we're never going to get any conflicts from there. So does this work? Well, if we look at the benchmark, yeah, you can see a very clear difference there. It's about a speed up of 100 times. And if we zoom out in time, we can see that we haven't got any regressions there, right? The performance has stayed good. Incidentally, if we zoom in a bit, we can see quite a lot of jitter. Now, this isn't necessarily bad, but it is just indicative of running on cloud virtual machines where your performance is a little bit unpredictable between each run. But for macro benchmarks, it's still very useful. You know, we can see what we're optimizing from, and now what we've got is very clear on these graphs still. So let's kind of dig into what we've done. Well, we've reduced the complexity from about 02N to 01. But the behavior has changed because now the ID always increases. There's also something subtle that we've introduced, which is if we call this the numeric limits uint64t max times, then this is going to wrap. But that gives us 18 times 10 to the 18. So is this really a problem? Well, probably not, because that's quite a lot of tracks or clips or plugins. And I was speaking with Timur about this, who had a similar issue when he was looking at read copy update and kind of monotonic counters. And he said that actually, if you do this, then you get 1,000 numbers. You could generate 1,000 numbers every microsecond for 300 years. So for most people, this isn't going to be a problem. However, if you're making a spaceship that might live for that long, or a satellite, then it could be an issue. The important thing here is that the contractor stayed the same, though. It still returns a unique identifier, and we've checked that with an assertion, hopefully a contract in the future. Okay, number 4, caching appropriate data. If data is accessed and manipulated in the same way frequently, it may be faster to store that data somewhere, right? So this introduces difficulties. We need to now have some additional data, which is the cache, and also whether the cache is dirty or not, right? So we've got this new relationship we need to keep track of. And we also need to know when we can clean the cache up. Is it in use anymore? Can we clear that data? And also, can we actually delete the cache entirely? When you have something like a Myers-Singleton pattern where you have a function local static and return that, then that's going to live for the duration of your program once it's instantiated. You might be able to clear the map or something, but there's still some memory in use. So it does often use additional memory, and that could be a problem, as we'll see later. So an example, again, from our code base, we have MIDI sequences, which are note events, note on and off, like you'd get from a piano. And it's quite a musical thing to do is loop them. And because we kind of iterate through them as they're played back, we cache the looped versions, so we don't need to deal with the behaviors around the loop points. And a simple way to do this is just store that loop sequence in a unique pointer. And then if that unique pointer is null or null pointer, then we create our loop sequence and then return that. Now all we need to do is when something that influences that loop sequence, like a note changes or is added or moved in time or pitch, then we just delete that pointer, and only the next time something needs that loop sequence are we going to create it. So that's an example of lazy initialization, which I spoke about before. Okay, on to our last technique, reducing memory footprint. So as we saw earlier, cache misses effectively stall the CPU and waste cycles, right? Because the CPU can't act on data that it doesn't have. So all of those clock cycles that are going by are just going to do nothing until the data is pulled through the cache and loaded into registers. So reducing the amount of memory a piece of code uses can reduce the amount of time it takes to execute. That's because it's likely to be in lower cache levels. And as we saw, lower cache levels are much, much faster. And if possible, we should use contiguous memory. And we'll see an example of why this is beneficial here. So I know this isn't exactly how CPUs work, but kind of it's nice to visualize it. Here we've got up the top is towards memory, so higher cache levels, and down is kind of low cache levels. And what we're trying to do is load stuff into registers. So if we have our data spread out like this, where we're interested in the green sections here, memory is pulled through cache in cache lines. So we're always going to read the same amount. So the data that we're interested in is only a small portion here. So if we kind of have to put in all this extra data, again, it's slow from high levels of cache, then it takes a long time to read the bits that we're interested in into registers. However, if we use some contiguous memory, it's likely to end up in our cache like this, and therefore we can just read it nice and quickly. So this is why it can be beneficial. Here's an example that I created just the other day, where I was creating a CPU usage graph, and this is essentially a FIFO. So we sample the amount of execution time and then add it to a list, and that list is only 1,000 long, and then we just plot that out in this graph. So DEC here, or double-ended queue, is the obvious choice because it works as a nice FIFO. You have a push front and a pop back, which is what we want to do. But I thought, well, is vector a better choice here? Because DEC allocates things all over the place, whereas vector always keeps the memory contiguous. So again, I'll just get rid of the Quickbench boilerplate here. And this was using 1,000 elements because that was what I was sampling here. And if we look at the results, we can see that both GCC and Clang vectors nearly twice as fast. So, even though DEC is the natural choice here, vector is still the better performing. And I was trying to push this because there's probably a point where every time you push something to the front of a vector, it has to shuffle everything around. There's probably a point where that becomes not the best way to do it, but I got up to something like 10 million, it was still quicker. So just the memory access patterns and the caching problems from DEC were probably causing the issue. So yeah, vector for the win. Okay. Now we're just going to try and pull this together. And this builds on a talk that I gave a couple of years ago, actually during the pandemic online, introducing our traction graph, which is our audio processing framework. So if you're interested in kind of more details, there's a link up there. You can check it out. But what we essentially end up with is a bunch of nodes that do some processing. So at the bottom, they could be, say, reading audio files. And then as we go up, they're summing together. C could be measuring the levels and then sending it off to the UI. And then A is adding everything together to output our audio device. So that kind of thing. But we need to figure out how to process this graph. And to do that, turns out the best way, and I go into more details in the other talk, but is to do a post-order depth-first search. And that means that we create an order by adding a node to an order the last time we visit it. So we don't add A initially, don't add C, but we add F, add C now because we're not going to visit it again, and then we add A. And when we rearrange our graph, we can see that we end up with this nice order where we only have forward-pointing arrows. If we did a pre-ordered depth-first search where we add a node to our order the first time we visit it, you can see we get these forwards and backwards arrows. And that's problematic because we can't process node A because it has a dependency on B and C, right? So it's not able to work on data that it doesn't have yet. So that's why post-ordering is the best approach here. So again, that's just kind of a quick background. So we can process this with a single thread if we just start at the top and go all the way through. But each node needs some memory to work on, right? We're going to read some audio files, some nodes together. Each of these nodes needs some memory. Now, for example's sake, I'm going to say they all need the same amount of memory. So we can just allocate them from a pool in a kind of just the simplest way, which is just, each node gets its own chunk of memory. And then we can process this using a single thread, and it's never going to be a problem. But there's going to be no race conditions, is what I'm saying, on the data. But if we think about this a bit more cleverly, we can say, well, if there's only a single thread processing these, then perhaps we can reuse some of that memory for nodes that have been processed and won't be used again. So we can do something like this. We can think as the thread is going through processing, but this is a pre-analysis stage, we can assign chunk 1 to D, chunk 2 to E, and then chunk 3 to B, because it's going to sum those together. But once we get onto processing F, theoretically, we don't need chunks 1 or 2 anymore. So we can reuse chunk 1 for F. C is grayed out because it's just an observer. It doesn't actually need its own memory. It's just monitoring some levels or something like that. Then once we get to A, that can reuse chunk 2. So we've now only used 3 chunks of memory, which is a lot less, 40% less than our worst case where every node has its own memory. But these days, we typically don't do things with just a single thread. We have multiple threads. So what happens if we do the same kind of pre-processing analysis stage and memory allocation, but in a worst case scenario when there's the maximum number of threads processing? Well, I've drawn the graph in its original orientation on the left-hand side, so you can kind of visualize this because it's quite complicated with multiple threads. But essentially, a thread could process each of the leaf nodes at the same time. So they each need their own memory. Then once they've all processed, we go up the next tier, and then we see that F needs some, also that F is a leaf node. So B needs some memory, which needs to take chunk 4 because all of the rest are still currently being used. And then once we process the final node, we can see that 1 and 2 have now been returned to the pool because they're not in use. So we could reuse chunk 1 to process A. So we've got some save in here, but it's not as good as we got with our kind of optimal single-threaded pre-analysis stage. But there is another way to do this, and that is rather than doing a kind of pre-analysis stage, we could do this at runtime whilst the graph is actually being processed in our real-time thread. So to do this, you'd rather than have a kind of a pool that's just being drawn from on a kind of pre-analysis allocation phase, and now you'd have to have this memory pool as some kind of lock-free data structure. So each node, as it's about to be processed, could kind of retain and release to the pool. And this kind of works like this. I've only done 2 threads because it's a lot easier to visualize. So it's similar to before, D and E take chunks 1 and 2, and B obviously needs to take chunk 3 because it depends on D and E. But imagine these finish processing at almost exactly the same time, just because of the way the threads are scheduled. We now start processing F and C, which means F can reuse the chunk that D had, okay, because that's not in use anymore. And then once we go on to A, that can reuse chunk 2. So we've gained a chunk of memory here as compared to before, so that should put less pressure on our cache and we should get more performance, right? Well, first of all, we need to think about this a bit. And it's difficult to reason about. And that's because there's lots of threads going on, this memory pool, and also the behavior probably varies a lot depending on the graph size. So how many nodes do we have? The structure, how deep versus how wide it is, and what are those dependencies? And also the node memory size. I mentioned that for simplistic slide where each of these nodes are the same size. But imagine you've got mono files being summed into stereo or surround or even like 64-channel Dolby Atmos. Each of those nodes are going to need different sizes of memory. And also, the number of threads might change, right? If you're using one thread, then we've got a very different situation to 2 or 16 threads. So what we really need to do is measure and benchmark, okay? We can't just say immediately which of those solutions is the best for this problem. And this thinking came about from a project that a user sent me that said, this is taking a lot more CPU than I would expect. So here's a snapshot of it, but that's really just the tip of the iceberg. So this graph was about 1,000 nodes, and typically most projects are between 1 and 200. So this was something a little bit different. So I created that runtime memory assigner, and then I profiled it. So here is the baseline case where each node just has its own chunk of memory. So kind of theoretically the worst cache performance. And you can see it's quite noisy, but then I profiled the other runtime assignment, and on the face of it, it looks better, right? It's slightly lower down. But actually, if we look at the scales here, we can see the original case beats this in almost every scenario. So what's happened? We know we're using less memory here, but the overhead of using less memory have outweighed any cache benefits. And that's because we have a lot of complexity in this runtime assignment. Those graphs have multiple layers of dependencies, and everything has to be allocated via this lock-free queue. So if there's lots of threads contending on that data structure, then they could be waiting. And also there's just more involved in kind of pushing this memory around and those references now. But this was for that use case. It might be different on more constrained platforms. If you've got a real-time operating system where thread scheduling is very reliable, it might be different, or embedded might be different. Or it might be different if you have different graph configurations. As I mentioned, more nodes, larger channel counts, larger buffer sizes. So it's quite often that people run a buffer size of 128, all the way up to over 2,000. So there's going to be a very different amount of memory used in these graphs at those buffer sizes. So what we might need is some heuristics of when to adapt. So we might need to think about all of these properties and say, well, this strategy is going to be best for this scenario. So that's where I kind of got up to last time I gave a version of this talk. But I've been thinking about it since. I thought, well, maybe there's another approach, which isn't to kind of allocate the memory or assign it at runtime, but it's to look more deeply inside the graph and have each node decide what memory it can use. So here we can see that D has a dependency on B has a dependency on A. So why can't they just use the same chunk of memory, right? Because D only has a single output, therefore no other node is going to be reading from it apart from B, and so on with A on B. So I know that sounds a little bit confusing, but if we do this, it works out that we can use the same chunk of memory for D, B, and A, and then the rest of the assignment kind of works in a similar way before. Now, we're doing kind of 3 threads here because that's the worst case for this graph. There's only 3 leaf nodes. But we can see that our threads come in and they're only processing chunks 1, 2, and 3, so different chunks of memory. And then as we go through the graph, D isn't being processed while B is being processed, and so on. So if we kind of sum up the amount of memory used in this approach, it's actually only 3 chunks. So we're back to our theoretical maximum, but we don't have this runtime overhead anymore. This can all be worked out beforehand. So D can say, I've only got a single output, therefore B can use my output. Now, there's some pros with this. It's in this example, the same memory usage as a single threaded pattern, but also it allows other optimizations. So where you have a node that's perhaps summing multiple nodes together, if it uses the same memory, it doesn't have to clear itself and then add in the first node anymore because it's already using it. It can just sum in others. So that can give you alternative optimizations that you can't really get with the patterns I showed before. But there are some cons here. It's harder to implement because it has to be implemented essentially per node. So each node needs to look at its inputs and see if it has an output, see if it has an input node that has only itself as an output, right? That's the only way you can do this. Because if a node has multiple outputs, then multiple things might be using that memory, so you can't overwrite it. And therefore, there's additional complexity to find these nodes. But again, this happens pre-processing, right? It's not strictly like a runtime cost. So I went back to this example and I thought, well, how much memory can I actually save with this? So I was going for about 30 megabytes in this kind of 2000 buffer size, and I managed to get it in half with not that much effort. There's still more memory to be saved here. This was just how far I've got at the moment. And I thought I'd get this far and then figure out if it's actually making any performance changes. And it turns out that, yeah, I mean, it's not huge, but it's about 7%. So we've got two things working in unison here. We've got those optimizations where we might be avoiding clears and copies, and we've also got less memory, so less pressure on our cache. So doing, perhaps thinking a little bit sideways of how to use memory better can give you some nice wins here. So I hope that kind of rounds everything out and gives you some tools and techniques for improving the performance of your code base, and remembering that this has to happen over time. So you got to think about performance as and take an engineering approach to it. So you can catch my past presentations and slides and things on GitHub. And there's also the Tracktion Engine code, which I talked about a lot, is open source. So you can go and take a look at that as well. Great. Thanks very much. I'll just see if there's any questions I can answer. So there are some. I think you don't have floating point exceptions. Yeah, there's all sorts of things that come in when you use fast math, and floating point exceptions is probably one of those. Yes, contracts. I tried to mention that a few times. Having contracts as an explicit thing in your code is really going to help. Do you need the memory downstream? Okay, so yeah, I think that was just preempting my last example there. How can the use of stood assume aligned help reduce cache misses? So assume aligned is quite nuanced. I've not used it myself properly yet, but I think the idea is that if you use stood assume aligned, your binary can be smaller because you don't have to generate the checks that check if the memory is aligned. So those checks will be instructions, and those instructions will need to be in your instruction cache. So I think the cache benefits you get are from your instruction cache, not your data cache. I hope that makes sense, David. There's a question that says, do you need fast math if you're trying to get the compiler to generate SIMD for non-float operations, for integer operations? Good question. I mainly deal with floats, so I've not really looked into it for integers, but I'm guessing not, because it's relaxing IEEE compliance and I think that mainly only applies to floats. I think you can probably get vector instructions on integers without that. And someone's posted a link. Great. Any more questions here, or should I head over to GatherTown? Yeah, I'll just wait another couple of seconds in case there's any more questions here. No, I think that's it. Well, thanks for attending, everyone. And yeah, hopefully see you around in the conference.